All right, I think we can begin now. So today it's oops. Now we're going into neural networks. So far, the first week was just introduction, so that was it. And then the second week, last week, we briefly just explored the very basics of machine learning. All the optimization and the a bit more complex concepts like overfitting, underfitting, recursive dimensionality, and some popular classifiers, some popular clustering algorithms. And I think the attendance check link will be different every week. And now, since we've covered the basic ML, we're going to now dive into the world of neural networks. So this week, today, we're going to talk about basic neural networks and the backpropagation algorithm. And starting next week, we'll be looking one model at a time, starting from autoencoder, then variational autoencoder, GANs and CNNs and whatnot. All right, so today's topic, deep learning frameworks. This will be just some of the frameworks that are popular that are out there. And then we'll start with logistic regression and then start adding one hidden layer to logistic regression and make it into a neural network, which is usually called a multi-layer perceptron, MLP, or simply just feed-forward neural network is also what it's called. And then how to train it with backpropagation, because we still need to optimize the model. So we're going to still borrow the concepts that we learned from last week. So we have a function and we need to learn the parameters of the function so that we can minimize the loss or the cost or, achieve the objective function. And the way to do it is called the optimization process using stochastic gradient descent. Still, the same rule applies, all the same rule applies today to the concepts that we're going to learn today. It's just that we're going to have to use something called backpropagation in order to train neural networks, because it's a bit more complex than just logistic regression that we learned last week. And then we're going to look at the concept of Autograd, how packages like PyTorch or TensorFlow or JAX, like those kind of automatic differentiation algorithms help us do differentiation automatic, how they can do it for us instead of humans doing differentiation. Machines do it for us. Okay, I'm going to mute everybody. Right, so deep learning frameworks. So there are, these two are probably the most popular ones out there these days. But there were some other libraries that were being actively developed back in 2014, 2015, I guess maybe up to 2016 or 17. So Theano is probably the first popular deep learning framework. Before Theano, people probably had to code CUDA codes themselves, like AlexNet, the author of AlexNet, Alex Krizhevsky, probably wrote AlexNet from scratch using CUDA, GPU CUDA code, a CUDA library framework. But Theano was developed by engineers in Yoshua Bengio's lab. So Yoshua Bengio's lab hired an engineer to develop a deep learning library, which was the very first deep learning library, probably the open source version out there, which was called Theano. And then it was maintained, I think it was maintained up until like 2017 or 2018. And then around 2016, 17, like big giant IT companies start to develop their own deep learning libraries. So Google developed TensorFlow, and Facebook, or actually Meta nowadays, Facebook back then adopted Torch into a PyTorch. So they started to support PyTorch development. And MXNet right here was a deep learning library supported by Amazon. I'm not sure what happened to MXNet these days. I'm not sure if people are still actively using it. Caffe was a deep learning framework written in C++. So Theano was written in Python. TensorFlow and PyTorch also, they were all written in Python. Caffe, on the other hand, was written in C++. Torch, actually, before PyTorch, there was Torch. And Torch was written in Lua, which is another language. And Torch was adopted by DeepMind before they were acquired by Google. So all the early Atari game agents, Atari game simulators, they were all written in Lua, and they had to convert to
TensorFlow, because now they were since they got acquired by Google, they had to use TensorFlow. So that happened. And yeah, I'm not sure even Caffe is maintained these days. But these days it's just either TensorFlow or PyTorch. And academics usually use PyTorch instead of TensorFlow, which has a lot more boilerplate. Right. So there's TensorFlow 1.0, and then there's PyTorch. And TensorFlow 1.0 is a compile the model, then it's a compile then execute. So compile then execute. So you can't change the architecture of the model as you train your model, or as you optimize your model parameters. Once you write your model architecture, whether it's going to be CNNs or RNNs or whatever neural network you prefer, you design, you write it, and then the TensorFlow will compile it, and then compile it into a bytecode that can be run on GPU. And then once it's compiled, you cannot change it as you train the model. So it's a bit static framework, and it has a big boilerplate. And then it's supposed to, because it's compiled and then executed, so all the compilation is done first, and then the rest of it is just running it. So it's supposed to be fast, and it's good for production, like large scale production for companies serving AI models to users or clients. Compared to TensorFlow 1.0, PyTorch, which came from Lua, is a compile as you go. So you can change the architecture of the model as you train your model. So during the optimization process, you can change the architecture, you can change the dependency tree of the variables. It's a very flexible model. So that's why people prefer PyTorch compared to TensorFlow when you're developing a toy model, or when you're playing with your model architecture. It has a smaller boilerplate compared to TensorFlow. Because of these, because of the compile as you go philosophy, it's supposed to be slower than TensorFlow. But this is all back in like 2017, 18, 19. Not sure. Probably these days, PyTorch has been heavily optimized since then. So maybe it's not as slow as it had been before. And as good for research, because you can implement your ideas, and then just run it, train it in a very small amount of time frame compared to TensorFlow. So TensorFlow, right? Okay, before we move on to TensorFlow 2.0. So TensorFlow used to be the de facto model, when developing deep learning models, but now, starting from 2018, 2019, PyTorch has taken its place. So you can see the graph here. It's the number of unique mentions in papers that were submitted in or presented in the so-called AI conferences or machine learning conferences. So you can see like ECCV, ACL, NAACL, ICML, all these well-known conferences, and the papers presented in those conferences, and how many times each paper mentioned TensorFlow or PyTorch. You can see the number of PyTorch being dominating TensorFlow as of mid 2018, I guess. So yeah, so the hard line is PyTorch and the dotted line is TensorFlow. So before 2018, mid 2018, it was mostly the dotted lines were over here and here, but now starting from mid 2018, like around the 2019, so it's PyTorch up here compared to TensorFlow, PyTorch up here compared to TensorFlow, PyTorch up here compared to TensorFlow. So you can see that it has gained popularity, and probably these days people rely on PyTorch way more than TensorFlow. I mean, I guess the gap between TensorFlow and PyTorch has even probably grew, or instead of decreasing. And so yeah, this is another graph that even papers on arXiv, the number of mentions in PyTorch compared to TensorFlow, PyTorch is catching up. So this is like 2019. So 2019, before 2019, like up until here, the PyTorch was mentioned less number of times than TensorFlow, even on arXiv papers. But starting from 2019 March or May here, it's catching up, and probably these days it's it's probably reversed the relationship between the two. So TensorFlow has actually saw that the PyTorch was gaining popularity, and then PyTorch, because of its flexibility, TensorFlow tried to mimic the behavior of PyTorch. So they adopted a compile as you go philosophy. So trying to be similar to PyTorch, and so they have this called eager mode, so which is compile as you go or lazy compilation. So you can also train, you can also change the architecture of the model or dependency of the variables in your model architecture as you train your model. So it's becoming quite similar to PyTorch, but then there's probably no reason to use TensorFlow anyway, because if it's like PyTorch, then we can just use PyTorch. So TensorFlow 2.0 was like that, and then came something called JAX around 2018 or 2019. So JAX is a language, or it's not like a library. The TensorFlow is a library. PyTorch is a library. You have a bunch of ready-to-go models in PyTorch and TensorFlow. You can just call CNN, you can just call RNN, you can just call transformer, But JAX is not like, JAX is like more like a NumPy. And then, so it's JAX is like a NumPy that runs on GPU, and it supports higher order differentiation. So if you want to compute like not just Jacobians, but Hessians, like second order differentiation, third order differentiation, which is not supported by PyTorch or TensorFlow, you can use JAX. So you can use a bit more complex computations. And so JAX is like that. It's like a NumPy on GPU. And then probably you need a library that is built upon JAX, which is called Flex. So Flex is like TensorFlow or PyTorch. Flex possesses a lot of off-the-shelf models like CNNs, RNNs, transformers. So it's gaining a lot of popularities. Flex and JAX, they're gaining a lot of popularities, especially inside Google. So researchers in Google Brain now probably exclusively use JAX and Flex. They no longer use TensorFlow at least in Google Brain. So if you want to learn new deep learning libraries, might be a good idea to learn Flex. I mean, JAX and Flex, they go together. So JAX and Flex and PyTorch at the same time. I mean, PyTorch, probably everybody knows about PyTorch. I mean, after this class, you'll be pretty familiar with PyTorch. So this cover will get you covered. But if you want to learn one more language or one more library, then JAX and Flex would be a good choice. Especially that it is different from PyTorch because it supports higher order differentiation. So sometimes if you're interested in doing some science with deep learning or some a bit more unorthodox or okay, I'm gonna mute everybody. Some unorthodox research that requires higher order differentiation, then you can't do it with PyTorch, so you must use JAX and Flex. All right, so we're gonna start with logistic regression. We're gonna start from logistic regression and then build upon it to dive into the neural networks or hidden layer, multi-layer perceptron with one hidden layer, and then go into the backpropagation. All right, so we last week I said that we're gonna study a bit more about logistic regression, how it's derived. So this is the time to do that. So logistic regression is probably the most popular model in statistical studies. So statistical studies, so 통계에서 많이 쓴다 이런 얘기죠. AI가 아니라 이제 무슨 원래. So logistic regression is not usually used for prediction. Actually, it's used for statistical studies. You have a hypothesis, right? I think I need to mute everybody again. So you have a hypothesis, and then you want to test your hypothesis using, like confidence intervals or the power, using the alphas, computing the alpha value of 0.09, 0.05, 0.01, and then you have the confidence. Like the logistic regression is used for that purposes mostly. It's not used for like doing binary classification actually. So it's a very well-studied model, and I looked it up, and it's been used since like 19th century. So it's for like, 200 years old. And it's used for analysis of coefficients of predictor variables. So predictor variable being, we have
if you're predicting like whether a person will get a cancer or not, and the predictor variable will be your gender, your weight, your whether you smoke, your age, that kind of stuff could be your predictor variables. And then you want to see which predictor variable is more correlated or less correlated with the outcome, the cancer. Then you have that is your hypothesis, and then you train logistic regression to fit the model, and then study the coefficients. So, and the predictor variables, they're sometimes called explanatory variables. In machine learning, it's usually called features, or in statistical studies, sometimes it's called independent variables. Right. So logistic regression looks like this. So the outcome, the probability of something happening, some event happening, it could be the patient having a cancer, or coin flip, seeing your coin come up on heads. Anything that is a binary output, binary outcome, you can use logistic regression to guess the probability of that event happening, which would be P. And it's 1/1 plus B, which is the base. So it's usually B is just natural constant E. B to the power of minus this here. So it's you can actually convert it into a vector form. So your betas will be the coefficients, and so there's beta vector inner product with your x's. So x1, x2, all the way to xm. You can consider there's x0, which is 1, abbreviated here, like ignored here. So you can turn this notation into beta inner product x. So we'll actually use this notation more often later. And so your logistic function looks like this. So if your logistic function, if you simplify it into a univariate situation, 1 plus e to the minus beta x. It's just these are not vectors. These are not vectors. Not vectors, a scalar. Then when you change your variable input variable x, the values of x, then you'll see a graph like this. So when x equals 0, it'll be exactly at 0.5. It'll be at 0.5. And as you increase your x, it'll increase the output, or the logistic function's output y, or the p, we'll call it a p. The p will increase all the way up to 1. Like as you increase and increase, the ceiling, the upper bound is 1, and upper bound is 1. And as you decrease your x, the lower bound will be 0. Will be 0 here. So it's a perfect model to model a binary outcome, because the output p will always be between 0 and 1. Right. So how is it derived? How was it derived from common concept like probability? So the win probability, we're just going to call the probability P a win probability. Like suppose that you're doing a gamble. 도박을 한다 치면은 돈을 따는 게 이기는 거고, 돈을 잃는 게 지는 거니까, 이제 이것도 바이너리니까, 이진분류니까 이제 승리의 확률이라고 합시다. So it's win probability. So in gamble, you either win or lose. So it's a binary situation. And your probability it lies in this range, 0 to 1, just like here, 0 to 1. You want your win probability to lie between 0 and 1 range. And you can convert your win probability into win odds. So odds is like this. It's a ratio between you're winning and you're losing. So this is your winning, and this denominator is you losing. So it's a ratio between win and lose. And the more likely that you win, the higher, the larger your odds will be. So if your win probability is 0.8, then your winning your odds of winning would be 4. So you are 4 times more likely to win than you losing. So that's what it is. If your win probability is 0.5, then your winning odds would be 1. So it's a 1-to-1 ratio. There's a 1-to-1 chance. It's 50-50 basically. It's a 1-to-1 chance of you winning or you losing. And if you have a win probability of 0.1, then you're like this much likely to win compared to losing. So it's 1 versus 9. So the good thing about odds is that the range is no longer confined in 1.1 to 1, 0 to 1. It's now 0 to infinity, because your odds will be As you increase your P, is actually the graph is here. As you increase your P all the way to 1, your winning odds will increase all the way up to infinity. So there's the upper bound of odds is infinity, but the lower bound is actually 0, because as you decrease your P, your probability, it is going to be capped at 0. So the range is a bit more free, like more freer, like it's more liberal. Then you have odds, because you're not still satisfied with your range being 0 to infinity. The reason that we're actually freeing up the range is because when you want to model something, like when you want to have a function whose outcome is 0 to 1, then your coefficients of your function, the parameters of your function, needs to be very, very carefully tuned. The model, the architecture, the framework, the functional form of your function, the form of your function also needs to be very carefully designed so that your output of your function has to be 0 to 1. For example, if you assume that your model is like a linear function, you have like a beta 0 plus beta 1 times x1 plus all the way to beta m plus xn, and you have your output P. And if you want your P to lie between 0 to 1, then you need to be very careful with your choice of your betas. You need to be very careful with the values of the beta so that your output has to lie between 0 to 1, which is very, very difficult thing to do. But if your output is 0 to infinity, then it's a bit easier to tune your parameters, the betas, because your output is now a bit wider. But the ideal situation is actually we want the output of this function to be between negative infinity and positive infinity, because that's how usually the linear function behaves. It's between negative infinity to positive infinity. So we want to actually free this even more to negative infinity to positive infinity, and the way to do it is actually putting a log function in front of it. So you put a log function in front of the odds. So log of odds is called logit. So it's another name for log of odds. Logit and log of odds are the same thing. So you put log function in front of the odds value, and now that becomes a bit more freer. So when P equals 0.8, the odds was 4, and then you put log in front of it, then it will be this value. And when the P was 0.1, the log of odds, the odds value was 0.111. And if you put log in front of it, then it becomes like this. So now you can see that as you move your odds from 0 to positive infinity, all the way to positive infinity, your log of odds, or your logit, will fall in the range between negative infinity and positive infinity. So the range of log of odds, or logit, is between positive infinity and negative infinity. So now this value, the logit value, can be easily approximated with some function, some polynomial function. It could be linear function, it could be second order polynomial function, third order polynomial function. It's, you name it. But for the sake of simplicity, we're gonna approximate it. We're gonna model this value, logit value, with a linear function. So if we put logit equals some linear function like this, then log of P over 1 minus P equals this, because we said that we're going to approximate it with a linear function. And then if you do some simple algebra, you put the log, you eliminate the log by doing exponential on this side, and then you reverse the denominator and the denominator like this, and then you have this value. And then you shuffle the P's around so that you have only one P in this equation, then you get this. So you have like this. And then if you simplify this again, then you get this. You divide the denominator, both numerator and denominator by this term, then you'll get this, where B equals E, actually. So where B equals E. So this is your logistic regression, right? So this is the logistic regression. So you can see how it was derived. You start from the probability of something happening, when you're winning at a gamble, or some patient having a cancer, or someone dying, whatever, like some binary outcome. So you have a binary outcome variable P, and you want to model it with a linear function, but then you want to do it
to do it in a more easier manner. So you first change the probability to odds, and then you put log in front of odds to make it into logit, and then you set the logit to be linearly approximatable, so that this is here, and then you you shuffle the terms around, and then you get this. So far, so good, right? Right, and then if you convert it into a vector form, then you get this. So the betas actually has become theta here. It's the same thing, beta, all the betas. As a group, we just call it a theta, a trainable parameter. And then you have your input x. Right. So instead of calling it p, we're just going to call it a h theta x, which means that the outcome of this function is parameterized by this value, this variable theta, and then it has the input x, right? And basically what this function is this. It's a probability of y being equal 1, which means that winning. So like how likely, what's the probability of you winning given this input x parameterized by theta here? So far so good, right? It's probably very easy. Right, so logistic regression, so instead of doing a statistical study, this is machine learning course. So we're gonna use it for binary prediction. And we're gonna start with a image classification example. So we can use logistic regression for doing image classification. You don't have to use CNN all the time. If it's simple enough, you can just use logistic regression. So for example, let's say that you are given an image and you want to classify it into a man or a woman. So let's call that being a woman is 1, so y equals 1 is woman, and y equals 0 is men, and then you want to classify it. So the way you do it is you first have to, well, I mean, you're given an image. Let's assume that this is 128 by 128. The resolution being 이제 12818상도의 이미지, 흑백 이미지라고 생각을 하는 거죠. So it's a black and white image of resolution 128 by 128, and then you put the pixel values directly into this x place. So you first have to actually linearize it. So you take the first pixel, here, and then you take the first row, second row here, third row, fourth row, all the way to the 128th row. So your input vector would be 128 squared, which is about 16K, right? So your x value, your dimensionality of your input variable x would be 16,000 dimensional. It would be a 16,000 dimensional vector, right? So yeah, image representation vector. So you can assume that this is 16K. And since it's black and white, the values in your values of each pixel would be 0 to 155, 255. 255 being like white and 0 being black, and then anything between would be gray, like light gray, like middle gray, and like bright gray, something like that. But for the sake of simplicity, we're just going to say that the variables would be either 0 or 1. The pixel is either black or white. So it's just for simplicity. So you have a 16,000 dimensional vector with binary value, 0 or 1, in each place, in each pixel. And what we need to do is we need to optimize this theta value in order to correctly predict or correctly classify whether a given image is a man's image or a woman's image, right? And since x is 16,000 dimensional vector, your theta will also be it has to be a 16,000 dimensional vector. So you have a lot of parameters to tune, actually. So we need to estimate theta, and what we're going to use is we're going to use a principle called maximum likelihood estimate, which is called MLE. In Korean, I think it's 최대 우도법, 최대 우도 측정법 뭐 이런 걸로 알고 있는데 이제 배우신 분들은 이제 기억이 나시겠죠. So we're gonna use maximum likelihood estimate principle in order to train or in order to optimize the theta so that you can maximize the likelihood of when given a woman image, you go here. When given a man's image, you go here. I mean, actually. Yeah, when given a man's image, you go here. So you want to maximize the likelihood of this happening. For women's image, having an outcome y equals 1. For men's image, having an outcome of y equals 0. And you want
So that's what we want to maximize. So that your classifier, your binary classifier, which is logistic regression, is as accurate as it can get. Right. So, and the way we're going to do it is, of course, we're going to learn from data. So because the data is sampled from reality. So 이제 현실에서 이제 실제 세상에서 가져온 데이터가 이제 진짜 실제를 세상을 반영하겠죠. 실제 세상을 반영하니까 그게 이제 ground truth라고 생각을 하고 거기로부터 이제 이 모델을 학습을 한다 이겁니다. So these training pairs, this will be some image and women or men or female, women or men. Actually, let's just call it male or female. A bit more easier to handle. So it would be male or female. This would be male or female or male. This would be like so it's an image and a pair of image and its binary output, binary label. And since they're sampled from reality, that's what we want to mimic. We want the model to mimic or follow the reality. So we start from the log likelihood function. So you can remember that this was our probability function form, the logistic regression function form. So h theta x equals 1 over 1 plus this value here. And since we have a lot of training samples, what we want is that when you put x1, so let me erase some stuff here. When you put x1 here, then you want your h theta x, or let's call it a y hat. Let's call it y hat. You want your y hat to be this y1, right? When you put x2 here, then you want your y hat to be y2. When you put x3 here, you want your y hat to be y3, right? That's what we want to see happen with the logistic regression function. So that's what we need, and that is how we want how the theta should behave. Given a proper theta, when given x1, the output would be as similar as possible to y1. Like if y1 was like, since this is a binary variable, all the y's would be either 1 or 0, right? Let's call this 1, 0, 1, all the way to like maybe 1 here. Then when you put x1, you want your h theta x, the value, to be as close to 1 as possible, like hopefully 0.99 or 0.95, something like this, And when you put x2, you want your function output, the outcome of the function, to be as close to 0 as possible. So hopefully like 0.01 or 0.05 or something like that, right? So you want your theta to behave like that. And the way we do it is we first put x1. So we first, here it is xi actually. So we put x1 and y1 into the function, x2, y2, y1, y2 to the function, x3, y3 to the function. And then so when you put x1, so when you put x1 in here, your h theta x will be some value, maybe let's say that was like 0.35, because your theta is messed up. Your theta is not a proper theta. So maybe when you put x1 in here, your output was 0.35. And when you put x2 here, maybe your y1 hat, maybe your y2 hat was 0.78, because it's, the theta is not properly tuned. So this could happen. So you're fine with that. First of all, you're fine with that. So what you do is you put all these values, and then so what you put all these values here. So, and then you do it the same for x3 all the way to the xn, and then you multiply all these likelihoods. So this is likely. So when you put x1, what you're doing is you're actually calculating the likelihood of this function. So which is y1 hat, and when you put x2, you get y2 hat all the way to yn hat, which would be some value, some untuned, unfine-tuned value. And then you multiply all of them together, because you're given the entire data, and you want to maximize the likelihood of seeing all these data at the same time, like a joint probability. And since all these samples, sample 1, this is sample 1, this is sample 2, this is sample 3, all the way to sample n, these samples are independent, because we always assume that the samples in the training sample are IID, like independently identically distributed. So you assume that all these samples are independent. So the joint probability of seeing all these data at the same time, you simply just multiply, because they are independent, right? So you multiply this. So here, this is basically h theta xi. So what you're doing is you're multiplying this time x1 times there's 1 plus e to the minus theta transpose x2 times 1 plus e to the minus theta transpose x3 times all the way times, until you get xn. And yeah, so that's basically it. And you model this. So once you did that, you model this with a Bernoulli distribution, because Bernoulli distribution is the one that we use to model a binary event, right? So if you're not familiar with Bernoulli distribution, you can look it up on Wikipedia, but its form is like this. So you have an output. So you have an output, winning output, and then you have the actual event here, and then you have a losing output and the losing event, and then you just multiply them together, and that's your Bernoulli distribution. So since we are modeling binary event, we simply just we simply model this with a Bernoulli distribution, right? And then since when we usually optimize parameters, we put log in front of it because it's easier to handle, because of all the underflow, to prevent the underflow from happening, and also because of the multiplication. If you put log in front of it, it'll become a summation, right? So it's easier to handle. So you put log in front of it, and then you normalize it by dividing everything by the large n, the number of samples. So 1 over n log. Then you do the same thing with 1 over n log here. Then that becomes this one. So 1 over n summation of the log probability or log likelihoods. And then when you put log in front, log here, then you get this, right? You get this. You put the log of h x y 1 minus h x minus y. This becomes right here, right? So easy peasy. So now you can see that this actually is a negative log likelihood, actually, because we put here, it was log likelihood function. It was just log likelihood function, but we put negative sign in front of it. So now it becomes negative log likelihood function. And the reason that we put negative sign in front of it is because we want to minimize. Usually, if you remember what we talked about last Tuesday, we want to minimize a loss or cost function. Like achieving training a function for objective function is usually done by minimizing a loss function or a cost function. So we need something that can be minimized. And since we want to maximize the log likelihood, we want to minimize a negative log likelihood. So that's why we put negative in front of it, so that we can do a proper gradient descent with this as a loss function, with the negative log likelihood as a loss function. And if you guys are familiar with cross entropy loss, then this is exactly the cross entropy loss, right? So if you have learned cross entropy loss from some other machine learning class, you can see this is exactly the same thing. So cross entropy loss is basically just Bernoulli distribution, put a log in front of it, and then putting a negative sign in front of it. So that's exactly the same thing. So here we have y hat n and y hat n here. So it's pretty dirty around here. So your h theta x, the function's output will go here, and also here, and your yn is given from the data. So it's given from the data. So the only thing you can control is the theta here. So the theta is embedded inside this y hat. So y hat is actually derived from theta and x, right? xn. Theta and xn. So xn is also given from the data. So the only thing you can control is theta. And the way so if you control your theta, or if you optimize your theta properly, then your negative log likelihood will be minimized. And then conversely, your log likelihood will be maximized. That means that your function will behave in a way that you prefer. When you put x1 into your function, the output will be as close to y1 as possible. When you put x3 in your function, the output will be as close to y3 as possible, right? So that is how we do it. And the reason that, I'm sorry, the way we optimize the theta, which is embedded inside here, is done by gradient descent. And we've learned gradient descent last Tuesday, so I'm just going to skip this. So far, any question? So this becomes our loss function. So this is our loss function. And loss function usually had y and y hat, right? If you remember what we talked about last Tuesday. Loss function is basically comparing a true y and your predicted y. So true y here, your predicted y here, and your predicted y comes from a function of x, function of x parameterized by theta, and this is exactly that. So what you need to do here is that you need to have a grade, you need to compute a different, you need to differentiate your loss function with respect to theta, which is here. And then you update your theta step by step, So far, any question? 왜 NLL에서 마이너스 4를 하는지. NLL에 그러니까 이제 우리가 원하는 거는 그레디언트 디센트를 한다는 거는 어떤 로스 펑션을 최소화한다는 거잖아요. 근데 지금 얘는 이거를 가지고 최소화를 하면 안 되죠. 왜냐면 우리는 이제 로그 라이클리후드를 맥시마이즈 하고 싶단 말이에요. 이제 이름부터가 맥시멈 라이클리후드 에스티메이션이잖아요. 그러니까 최대 이 펑션을 최대화하고 싶은 건데 우리는 이제 GD로는 최소화를 하기 때문에 그 프레임워크에 맞추기 위해서 일부러 이 앞에다가 마이너스를 붙인 겁니다. 그래서 이제 얘를 최소화할 수 있도록. 그러니까 이제 얘를 최소화한 거는 얘를 최대화한 거잖아요. 그것 때문에 이제 마이너스를 붙인 겁니다. 네, 좋습니다. So yeah, you'll run into negative log likelihood functions all the time, in it, not just for binary output, but for multinomial distribution, like multi-class classification, you still use negative log likelihood. All right, we're going to move on to neural networks. So neural networks are models that consist of neurons. So this is an actual neuron in your brain, or actually not just brain, anywhere in your body. So neurons, they gather information, or actually not information, like electrical energy from surrounding neurons, like energy coming from here, like 전기적 신호가, electric signal is coming from all the neighboring other neurons. And then if the collection of those electric signals are above a certain threshold, 이제 어떤 임계치를 넘으면, 역치를 넘으면 above a certain threshold, then the electric signal inside so this neuron will fire electric signal to the next neuron. So the collection of, if the collection of electric signals inside the neuron is above a certain threshold, then that neuron itself will fire the signal to the next neuron. So it's the signal is propagated to the next neuron, and the next neuron will do the same thing. Like the next neuron has a lot of branches to connect it to other neurons, and if that electric signal is collected, and the collected electric signal is large enough, then this neuron will also fire. And so it's fire. So the signal is propagated inside your brain all the way to, to your body, throughout the entire system of your body. Question, 실제로 딥러닝 할 때 크로스 엔트로피 로스를 출력해보면 작은 양의 실수가 보이는데 왜 그런 건가요? Well, actually, if you calculate this, then you will get a small real value. So usually when you do gradient descent, you don't actually do stochastic gradient descent with a mini batch. So for example, if your mini batch size is like 16, for example, then you're using 16, 1, 2, 3, 4, 5, 6, 7, all the way to x16, y16. You're using 16 values, 16 samples at a time. You put 16 values here using a for loop, like y1 hat, y1, y2 hat, y2, y3 hat, y3. You can do that using a for loop, and then you calculate this value, and then divide by 16. Then you'll get some scalar value, right? I think that's what you're asking. 맞나요? 혹시 제가 답을 한 게 질문에 답이 되나요? 아, NLL이 음수라고 이해할 때 NLL이 음수일 수도 있고 양수일 수도 있겠죠. 왜냐하면 지금 여기 있는 로그 값이랑 뭐 이런 것들이 조합으로 인해서 뭐 어떤 값이 나올지 모르니까. 네, 어찌 됐든 간에 이제 최소화시키는 게 중요합니다. Right, so we were talking about neurons and how it fires electric signals to the next, and then there's propagation of electric signals all over your brain. Same deal with artificial neurons. So artificial 이제 우리가 그 뉴럴넷을 한국말로 인공신경망이라고 그러잖아요. 그러니까 이제 진짜 신경망이 아니라 가짜다, 인공이다 이거죠. So the way that artificial neuron works is very similar to actual neurons like this. So there's a bunch of signals coming from its neighbors. Well, actually, not neighbors. It's just input. So there's a bunch of signals coming from its input. So there's signal here, like all the bunch of different signals. And then if that collected signal inside here, so it's a summation of all the signals coming from different inputs. If that summation, the collection of signal is large enough, and if it's like above a certain threshold, which is controlled by the activation function, then it'll output some value. So here, usually in artificial neuron, like if we deal with just one single neuron, then we usually use sigmoid function as an activation function. So sigmoid function here. I think we have, right, I think we're gonna do it ahead of a few slides. So sigmoid function looks like this: 1 plus e to the minus. Well, I'm just gonna call it x. So sigmoid function is exactly like the logistic regression graph here. We had this like this, right? So if x equals 0, it'll be 0.5. If x is above 0, then it'll be moving towards 1, which is the upper bound. And if x is smaller than 0, then it'll move towards the lower bound, which is 0, right? So that's the behavior of the sigmoid function. So it looks like it's like there is like it kind of looks like it's simulating a threshold. 그러니까 이제 약간 이게 어떤 역치를 표현하는 그런 함수로 보이잖아요. It looks like it's trying to mimic a step function like this, right? It's not as hard threshold as the actual step function, because then the behavior of this model would be very extreme. But so we want to use a bit more smoother threshold function, which happens to be the sigmoid function here. So if you imagine this being a sigmoid function, then this is kind of like an actual neuron in your brain. You get signals from a bunch of inputs, and then you sum it up, and then if it's above a certain threshold, like here, then it'll fire 1. If it's like somewhere around here, it'll fire values that are close to 0. Right? And the input signals are actually not just signals. It is actually controlled by independent weights. So the first input is multiplied by the weight 1, W1, and that becomes your W1, X1, the signal. This, just going to erase. So this will be W1 times X1. Here it's W2 times X2. It's all the way to Wm times Xm, right? And then you sum them up inside. So if we're going to do the image classification with a single neuron, for example, we can still do that. We can still do image classification, a binary classification with a single neuron. Then you can imagine this input values being the 16K dimensional vector with 0, 1, 0, 0, 1, something like that, And you multiply each pixel value with corresponding weights, and then you sum them up. And then there's bias, which is just 그 절편인 거죠. There's bias, and then you push, and then you sum them all up, and then you push it through a activation function, and then you have your output, man or woman, like this. Right here. This is the vector representation of the input image. Right. As I said, the sigmoid function is like this. So if you assume that the activation function is a sigmoid function, then actually this is something very similar to what we've seen before. This is an artificial neuron, right? This is an artificial neuron with
input x multiplied by w1, input x2 multiplied by w2, all the way to input xm multiplied by xm wm, and then you sum them all up with a bias, and then you push it through an activation function to get an output. So what is this single neuron? Like, what is the identity of the single neuron? The answer is, I mean, you can go to the next slide, but this is actually exactly the same thing as logistic regression, right? This w, you can assume that this is an x vector, this is a w vector, and then summing up would be w's transpose x, and then you push, and then there's b here, bias b here, and then you put that in here, x, the position x, then this becomes 1 plus 1 over 1 plus e to the minus w transpose x plus b, which is exactly the logistic regression. Y equals this. So if you think about it, logistic regression is actually just a single artificial neuron with where the activation function is sigmoid function. So you can see the connection between neurons and logistic regression. And if we increase the number of neurons, if we start adding hidden neurons, you can see the connection between how logistic regression is evolved into multilayer perceptron, right? So that's what we're going to do actually. So we put one extra hidden layer here with 4 neurons, 4 hidden neurons before we get to the output. So before it was just all the x's multiplied by w's, and then that goes directly to the output. That was before, but now instead of going directly to the output, we stop by these 4 hidden neurons. Well, it's not 4 hidden neurons. It's 1, 2, all the way to k with a bias. So there are k hidden neurons here. So when you do that, then you can see the connection has become way more complicated. Before it was just, x times w all accumulated here in the neuron, and then that was it. That was the end of computation. But here now, all the x and the w's are the multiple. The w transpose x is propagated here, also propagated here, also propagated here. So there's way more connections here. So let's assume that there are only 4 hidden neurons in your hidden layer. And so it's just, example, fit for a neural network with 1 hidden layer of 4 neurons. And let's assume for this time that all the hidden layer activation functions, so the activation functions of all these hidden layers are sigmoid function. And also the output should also be a sigmoid function because we're trying to do a binary classification. So you can see that here, this hidden neuron number 1 would get information from, will be collecting signals from the input signals from all the pixels, 16K pixels, and it will have its own corresponding W1, W2, W3, W4, all the way to W16K, right? And the information is collected inside. And same for the second neuron. Second neuron will have a different set of W1s. Well, actually, it's a different W1 than this W1. It'll have its own W1, W2, W3, all the way to W16K, and then you calculate the input signals, and then you accumulate it, you sum it up inside this hidden neuron. All the way same, right? Same here. So you have how many connections? You have 16K connections per hidden neuron, and you have 4 hidden neurons. So you have 4 times 16K connections, which means that you have 4 times 16K, which is about 64,000, right? 64,000 learnable weight parameters, basically. Yeah. So you can think of this as you can think of each individual hidden neurons as its own logistic regression. You can imagine logistic regression there being 4 hidden logistic regressions inside before you go to the final logistic regression. So there are actually 5 logistic regressions in this model architecture because you're all using sigmoid function as the activation function. So for example, let's assume, just like imagining things, let's assume that maybe the first hidden logistic regression model was calculating the probability of this image containing a long hair or not. It's like a win probability having a long hair. Maybe the second logistic regression was modeling or actually trying to see if the input pixel contained mustache or not, ribbon or not, had a makeup or not. 그 메이크업이 이제 화장이니까 화장을 했냐니까 이제
그 머리가 기냐 안 기냐, 이제 호수염이 있냐 없냐, 리본을 달았냐, 화장을 했냐 이런 것들을 이제 예측하는 또는 이제 분류하는 로지스틱 리그레션이 이제 안에 이 내부에 있을 수도 있다라고 이제 상상을 해보자는 거죠. 이게 다 어쨌든 하나하나가 다 로지스틱 리그레션이니까 지금. So you can imagine these 4 hidden logistic regression models performing each different like serving a different role, like long hair classification, mustache classification, ribbon classification, makeup classification, all of which are relevant to deciding whether this input image is a man or not, right? If the image has makeup, then probably it's a female image. If the input pixel has a mustache, then in all likelihood, it will be a male image, right? So they're all relevant factors. So when these factors were decided here, like long hair 0.1, mustache 0.9, ribbon 0.2, makeup 0.15, given information, I'm just gonna actually have to, right? If this was like 0.1, 0.9, 0.2, 0.15, then these 4-dimensional vector, 1, 2, 3, 4, 0.1, 0.9, 0.2, 0.15, these 4-dimensional vector will be the input to the final logistic regression. So the final logistic regression, which is a man or woman classifier, will be using a 4-dimensional input to finally decide whether the given image is a man or not. And given this combination, 0.1, 0.9, 0.2, 0.15, likelihood is that this is a male. But if the given input, but if the given input 4-dimensional vector was 0.9, 0.05, 0.1, 0.85, then this 4-dimensional vector given to the final logistic regression, then this will be female, probably, right? So that's what we assume would be happening. I mean, I'm not saying that this is actually happening, but this could be happening, you know. Right. So the final logistic regression model is a high-level logistic regression, meaning that this is not the decision factor. The final logistic regression, this model, is not deciding its decision. It's not making its decision based on raw pixels. It's actually making its decision based on these high-level concepts, whether the image has a long hair or not, whether the image has a mustache or not, whether the image has a ribbon or not, whether the image has a makeup or not. Like, these are the high-level concepts compared to the raw pixel values here. So it's a high-level logistic regression classifier. And by doing a backpropagation, this is already a feed-forward neural network with one hidden layer. We need to do a backpropagation, and based on this backpropagation, maybe this hidden logistic regressions will actually learn something very useful, like this. Like this is an example, but maybe this could learn. Maybe the first logistic regression could learn what, like whether the image has an earring or not, whether the image has like a beard or not. It could be anything based on based on your training samples. These 4 logistic regressions will be optimized to make a high-level to help the final logistic regression make the high-level decisions. So in all, it could make a correct male or female classification. Hopefully that makes it clear. Yeah. So this is a 4-dimensional latent representation. So it's no longer a raw pixel. It's a hidden, or like it's capturing the semantics of the image that is helpful for the model to make a final correct decision, male or female. Right. So as I said, there are so many connections in between the first input and the hidden layer. And to be very more specific, it's 4 times 16K. And so there are 4, and this should be 16K, because each hidden layer will be responsible for each row. Like this first row goes here. This, like the third row is responsible for the third neuron, so on and so forth. So, and since there are 4 neurons, there are 4 outputs here, 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 here. So there will be only 4 trainable weights between the hidden layer and the final layer. So all in all is 16K times 4, so 64,000 plus 4 learnable parameters. So that's what you need to tune. That's what you need to optimize. There are this many number of parameters that you need to optimize so that your model will behave, nicely. Right. So if you think about the fact that the activation functions are all sigmoid functions. So there's sigmoid function here. There's also sigmoid function here. So if you think about this layer here, there are W1, W2, W3, W4, right? If you focus your attention to only here, forget about here, only here, then in order to update your parameters, actually let's just call them thetas instead. So this is theta 1, theta 2, theta 3, theta 4, right? Theta 4. And you need to, the way you do gradient descent is that you update your parameters one at a time. Like theta 1 is theta 1 k plus 1 equals theta 1 k minus step size differentiation of, wait, is this correct? Yeah. Actually, I think I got the differentiation wrong. Here, though, you have the loss function, and you need to differentiate your loss function with respect to the theta 1, which is right here, like this. So that's what you need to do for all the thetas. Your old theta 1, theta 2, theta 3, theta 4. You need to set it. You need to run through this algorithm to update the thetas, right? In order to do that, you need to be able to do this differentiation, this partial differentiation, and this loss function here will be the same as the negative log likelihood function you have here, which is the same as right here, negative log likelihood function, or AKA cross entropy loss. So you need to do this, and you can actually do this because if you think about the y hat being here, y hat is determined by what? Y hat is determined by the thetas, theta 1, theta 2, theta 3, theta 4, and the outputs of the H1s. I'm going to call this, let's just call them A1. The output should be A1 here, A2 here, A3 here, A4 here. So simply it's just A, theta transpose A, and this one like this, which is y hat. So this will be your y hat, right? This will be your y hat. And the y value of y hat is determined by the theta 1, theta 2, theta 3, theta 4, right? So you can differentiate this whole thing, the loss function, with respect to theta, and then get some value, and then do this, basically do this, right? But the problem is that when you get to here, which has 16k times 4 number of parameters, you can no longer do this. You can't differentiate your loss function with respect to, let's call this W11, W12, W13, W14, like here. You can't differentiate your loss function directly with W11 because your output, your y hat, is not determined directly by W11. It's hidden somewhere inside. It's because your y hat is determined by A's and thetas, and the A's are determined by y. A's are determined by the W's. So you can't directly differentiate with your loss function with respect to W. So you need to apply a chain rule, right? So updating the W's, actually, so W is not theta. So updating W's here is pretty easy. You just simply do this, and this can be done even with your hand, actually, even with manually. But here, how to update this? This, not so easy. So because your NLL is not directly determined by the V's here. So that's where you need to use the chain rule. And that's where backpropagation comes in. So far so good. Any questions so far? 지금까지 얘기한 게 이제 로지스틱 리그레션은 바로 그냥 네게티브 로그 라이클리후드 로스 펑션을 바로 그냥 이제 파라미터에 대해서 미분을 할 수 있다, 편미분을 할 수 있다라고 했는데, 이게 이제 히든 레이어가 하나 끼게 되면 이제 요 레이어가 생기게 되면서 요 레이어가 이제 그 NLL에 바로 영향을 끼치지 않고 이제 간접적으로 영향을 끼치기 때문에 바로 편미분이 불가능하다. 그래서 체인 룰을 써야 되고, 그렇기 때문에 이제 백프랍이 이제 들어가게 되는 거다, 이 얘기를 하는 겁니다. Question from 신재호. 아까 로컬 펑션에서 양수와 음수가 뭐 나올 수 있다고 했지만 확률은 0일 값이고 확률이고 0일 무조건 음수 값이 결과에 나오는 거 아닌가요? 그런가요? 그거에 대해서 자세히 생각을 해본 적이 없어서 아직까지 잘 모르겠는데. Yeah, so your y value has to be, let's assume that your true y is 1. True y is 1. So this term goes away, and you're only left with this term. And your log y, your y hat n, your y hat n can be any value between. Actually, oh yeah, it has to be a value between 0 and 1. It has to be value between 0 and 1. And log of that is what? When you draw a log function, you draw a log function. It's this is 0. This is 0, right? This is 0, and 1 would be right. So this is 1. Log of 1. I'm sorry. Log of 1 is 0. I'm sorry. This is 1. So log of 1 is like, goes like this. Your y hat, this is your y hat n, and this is your log of y hat n, right? So your log of y hat n it's always negative, right? So this is always negative, and y1 is just 1. So this is only negative, and when you put the negative in front of it, then it'll be always a positive value, right? So that's why your negative log likelihood loss value is always positive, at least for when yn is 1. 재용님 이제 이해되셨나요? 네. Question from 김동수님. H1 옆에 적으신 H1은 이제 히든 뉴런. H1은 히든 뉴런 자체를 얘기하는 거고, 거기서 어떤 값이 튀어나올 거잖아요. A1이라는 값, 아웃풋이 있을 거다. H1에서. H2에서 튀어나온 값은 A2, H3에서 튀어나온 값은 A3, A4 이렇게 거기서 튀어나온 값을 말한 겁니다. 마치 여기서 Y 값이 튀어나오듯이. 28페이지가 어딘지 모르겠네. 네, 28. 바이어스는 인풋을, 네, 그럼 바이어스는 그냥 절편이라고 보시면 됩니다. 네. 무조건 더하기 1 하는 거예요. 그냥. 더하기 1은 아니고 더하기 B죠. 더하기 B인데 이 B가 이제 트레이너블 파라미터라서 이제 어쨌든 어떤 절편 값을 더해주는 거라고 보시면 됩니다. 네, 좋습니다. Alright, moving on to backpropagation then. So backpropagation is, well, I mean, everybody should know what backpropagation is when you're trying to train a neural network. So it's a very general like principle. So backpropagation can be used even when your neural network has a lot more layers than just one hidden one hidden layer like this. This here, we're using only one hidden layer, but here you can see that it's been generalized. There's input X all the way to, assuming that this is Y, your output. There are way more number of layers here. And in order to train a very complicated neural network like this, there's like how many parameters to learn? Like there's way more parameters to learn here. So in order to train all these parameters, you need to use backpropagation. So the loss function, or here is called C instead of L. It's the same thing. Sometimes we call it loss function. Sometimes we call it cost function. So, you know, it's the same thing. You can just assume that C is just loss function. It could be NLL. It could be MSE. It could be mean squared error. It could be mean absolute error. It could be cross entropy. It could be whatever you want. And you have a true output Y. So it's a ground truth label. And then there's your predicted label here, which is Y hat. And you can rewrite your Y hat as a nested function of neural networks, or neural network layers. Actually, this is your first layer with an activation function. Then you multiply that with your second layer with the second activation function, all the way to L-1th layer, L-1th activation function, final layer, final activation function. Usually, you know, if we're doing binary cross entropy, if we're doing binary classification, then at least your final output, final activation function has to be sigmoid function, right? The inner functions could be anything you want. It could be ReLU, it could be tanh, it could be whatever you want. So basically, this is Y hat. So you can understand why Y hat can be written as a nested function, like a function of nested functions, actually. And there are a lot of learnable parameters. WL, WL-1, all the way to W2, W1, they are all learnable, like trainable parameters. These are the parameters that you need to optimize.
So that's your function. And obviously what we want to do is we want to differentiate with respect to like all the W's, L, some W, L minus 1. Like you need to do this. So let's dive right into a one specific hidden layer here. So just one layer, just to make things simpler. Right here. So we focus on this L layer, and then it's L plus 1th layer, L minus 1th layer. And there are some number of neurons here, here, and here. And focusing on just one specific neuron here in the L layer. So let's assume that like we're looking at this here, here. So it's a neuron, so it's going to collect input signals from previous layers. So previous layers here, here, here. There's a bias, but from now on, let's just forget it. Let's just assume that there's bias every time. So we're just going to assume that we're just going to omit the bias term. So this specific neuron will collect inputs from the previous neuron outputs. So the previous neuron outputs will be multiplied by individual weights here. So for example, here, this weight is WLKJ, which means that this W belongs to the elf layer, and is being tossed to it is connected to the kth neuron. There's like one neuron number 1, neuron number 2, all the way to this is the kth. This is kth neuron. It's connected to K, and then there are a lot more weights that are connected to K. There's like WLK1 all the way to WLKJ, all the way to WLK, like large J, somewhere, you know. So that's what it means by WLKJ. And then inside the neuron, there's the sum of input signals. So all the input signals are weighted by W's, and they're summed up to get ZLK. And then when ZLK passes through a activation function, so there's activation function here, you get ALK. So far so good, right? These are just definition of different terms. So ZLK is a sum, then ALK is the activated value. Moving on. So when you want to do a derivation, when you want to differentiate with respect to all the way down to the bottom, which is X, your input, starting from the C. So we have C, and when we have a C or the loss function, and we want to differentiate it with respect to X, which is the C would be somewhere over here, right? Because it depends on the output and the predicted output and the true output, and your X is way over here. So all the weights in between needs to be taken care of, right? Needs to be accounted for when you do this, when you want to do a differentiation of the cost function with respect to the input X, so you need to break this down into it by a chain rule, which is way over here. Right. So your final C would be determined by the output A. And so you do this. And then your A is determined by Z, which is actually, there's an activation function hidden here. Then your summed input is determined by the output from the previous layer, which is this. And then the output is determined by your input, which also is determined, which there's a activation function hidden here, so on and so forth. You do this kind of chain rule all the way back to here. Z1 is determined by X. So Z1 is determined. Obviously, there's the very first W1 hidden here somewhere, because Z1 is actually W transpose X plus B, but we're forgetting about the B. So there's here. So this should be what? This should be W1, right? This should be F1. This should be WL minus 2, so on and so forth, right? So on and so forth. So you can see what's happening here. When you want to do a differentiation of C with respect to X, you can break the entire process of starting from the input all the way going up to the final output. You can see the entire process here. Right. So as I said, there's activation function hidden here, and then there's WL hidden here. Activation function here, WL minus 1 here, all the way to W1, activation function here, right? So all very clear, right? And this is what? This is DC dx. This is still DC dx. And so this is derivative, but when you put it into, when you re-express it into gradient, then you transpose it, right? The derivative and the gradient is like this, they have a transpose relationship. So you transpose the entire thing, rewrite it like this, you write it like this, and then you get the gradient here, which was here, and then you get the W1 here, right? Nothing complex, right? Now what we do is we define something called delta. So this delta is very important for actually running a backpropagation algorithm in TensorFlow, in PyTorch, wherever. So delta is defined like this. So delta is a error at layer L. So it's you can see that delta L is start from L plus 1, all the way to L, large L minus 1, large L, all the way to the final gradient, all the way to the final cost function gradient. So what it means that is that it's the error starting from the elf layer. This is the L here is the elf layer. So the error starting from the elf layer all the way accumulating all the way up to the final cost function. That is what this is. That is what delta L is. Or actually, you can reinterpret as how much the cost or the loss function changes when the input to the kth neuron at layer L changes. So before it was delta L, so it was a representative of the entire layer, but here it's delta LK, so we're actually just looking at one specific neuron at the Lth layer. So delta LK. So delta LK is how much your final loss function changes, your loss changes, when the input to the kth neuron in the Lth layer changes, right? So that is actually that is the definition of derivative, right? When you do a differentiation, you want to see how output changes when you change the input, right? So that is it. So that is what delta LK is. And yeah, you can write it like this actually. So delta LK is differentiation of C with respect to this particular neuron's input, the weighted sum input here. So yeah, so we had this here, we had this, rewrite it like this, and then we define the delta L here, and you can see that delta, when you write delta 1 all the way to delta L, it will become like this. Delta 1 is this here, delta 2 here, delta L minus 1 here, delta L here. And you can see some repetitions going on inside, because you can see that F2 all the way to gradient C is right here. So this is delta 2. And you can see that the final L is right here. This is delta L. So you can see the repetition going on. So there's like a recursive relationship between different deltas, right? So delta, if you look at deltas here, there's a recursive relationship between the delta L and delta L minus 1. So the upper layer's delta can be reused to calculate the lower layer's delta. Instead of calculating everything at all the, instead of calculating all the terms always over and over again, you can actually, if you start from the final layer L, go back down to delta 1, you can reuse the terms again and again and again and again. So you don't have to, recalculate all these terms all over again every single time. So that is why we use backpropagation. We start from the top and go back to the bottom, because then you can reuse the previous delta values as you go back down into the input layer. So that is the spirit of backpropagation. You can actually do forward propagation if you wanted to. It's just gonna waste way more computation. You can start from here, and then you go here, and then you go here, and then you go here, and which would be a waste of a lot of computation actually. Right. So that's the delta. That's the properties of delta. And you can actually use these delta to calculate this. This is actually what we really need. You need to, in order to update your WLs, what you need to do is W, for example, K plus 1 equals WL K minus step size, derivative of C with respect to WL K. This is what we need, right? In order to update the weights. And this can be obtained with delta very easily. You have the delta, you just simply multiply the AL minus 1, the previous layer's output, and that's it. And that's how you get the gradient here. I mean, if you're interested, you can actually just prove it by going through going through the definitions. It's pretty straightforward. Right. So yeah, the gradient is needed for this part. So if you calculate the delta, so for example, you start with here, you calculate delta L, you're here, you calculate the delta L minus 1, you're here, you calculate the delta small L minus 1. You repeat this process, and as you repeat the process at each layer, you can also calculate the gradient of C with respect to WL minus 1. Here, you can calculate gradient C with respect to WL minus 1, so on and so forth. And then, so that's how you move from one layer to the next layer as you update your parameters one layer at a time. So I hope that makes it very clear. Yeah. So yeah, so backprop is faster than forward prop, obviously, because you can reuse the previous deltas again and again and again. The problem is that you need to store these two values as you go from the final layer back to the input layer. And as you calculate the deltas, you need to have these values as well in order to calculate this so that you can update your parameters. So in order to do that, you need to have these values, AL minus 1, you need to have these ALs stored at every layer so that you can calculate delta, multiply this, get this, update your parameter, move on to the next layer, calculate delta, multiply this, calculate this, update your layer, update your parameters, so on and so forth. So you need to store them. This is actually just, if you're using sigmoid function, then it's sigmoid derivative of the derivative of the sigmoid is already fixed. So you can just, you can just, memorize them as a function. But these values, this value actually needs to be stored in your hidden layers. That is why when you do backprop, it takes up a lot of VRAMs in your GPU, because you need to store all these activation values for all the neurons in your entire neural network. And if you use actually a bit more advanced optimization algorithm like ADAM or Autograd or ADAM-W, then you need to store way more things than just the activation values. So that's why your VRAM will easily explode when you use higher order optimization algorithms. All right, so far any question? So this is the core philosophy of backpropagation. And the good thing is that you don't have to do this with your hand every time, because the library will do it for you. The PyTorch, TensorFlow, JAX, they all do this backpropagation for you. Once you define the architecture, the structure of your neural network, it just somehow memorizes this process, and then it does it for you. So we live in a good time. 질문 없으신가요? Right, then I'm going to move on. We got only a couple minutes left. So how it's done in PyTorch, how this whole backpropagation is done in PyTorch, and it's called Autograd. So there's a lot of Autograd packages like TensorFlow, Theano, PyTorch, JAX, MX, and all these are run in a very similar manner, which is using DAG structure, directed acyclic graph. So the computer does backpropagation for you, and a neural network is represented in all these libraries. Neural network is usually represented as a directed acyclic graph. So there's something like this. This is a directed acyclic. At least it's like a tree, but there can be many parents, but as long as there's no cycle, that's okay. So each node in the DAG contains a mathematical operation that you defined when you define the structure of your neural network. Each node contains a derivative of the math operation, so each node contains a math operation and its derivative at the same time. So for example, when you want to define a new operation in a PyTorch, you need to define the operation and its derivative at the same time. And the error signal is propagated all the way from the top, but the error signal being the derivative of the loss function or the cost function, is propagated from the output nodes all the way back into the input nodes. So there's a very simple depiction of how it's done. So your input, let's say that your input is a 2x2 matrix. It's 1, 1, 1, 1. And you have three variables, which is x plus 2 becomes a times 3 becomes b, and the averaging them would give you c. So this would be your DAG.
So there's X input, and your first node will be A, second node will be B, and third node will be C. But since node B is a bit complicated, inside PyTorch, it'll be actually broken down into 2 steps. So A, B prime, B, and C. And the B prime is just, power. So A times A. And the actual B is the multiplied by a constant 3. So B times 3, and B prime times 3, and then you get a final operation mean. So let's assume that this is your DAG. And what happens is that each function, each node has a mathematical operation, which is usually, I'm just making things up. This is not actual PyTorch, but I'm just making things up so you can imagine how things are done inside PyTorch. So for example, the first node will have a plus the addition function. So it's add constant. You're just adding 2. You're not adding by a variable. You're not adding any learnable parameter, trainable parameter. You're just adding 2. So it's add constant. Then there's power. Then there's multiply constant. And then there's final mean function. So each mathematical operation needs to be also come with a derivative. But add constant, multi constant, add constant, they don't have a derivative. This could have a derivative actually. Right, so once you have this, you do a forward. You put X in, and then you push it through upwards, which will be the forward process. So forward computing, forward propagation, and then saving input and miscellaneous for the backprop. So in order to do the backprop, what we needed to save was these two, or especially this, because currently we don't have any activation function in our DAG. So we need to store the activated values, or the output values, and then backward would be given data delta L, calculate this because we're going backwards, and then calculate this gradient with a L minus 1 if necessary. If at a certain node, if there's a learnable parameter, then you need to calculate this in order to update the parameter. But you can imagine that you can readily see that there's no learnable parameter here at all. It's just it's just computation. So right, so we start from here. We're doing backprop. So gradient, the differentiation of C with respect to B, which is here, then B with respect to B prime with respect to A. So you can break it down like here. So it can be broken down into this. The CA can be broken down into this. CX can be broken down into this. And you can see that here, it can be plugged in here. This can be plugged in here. And this can be plugged in here. So you can see already like a delta-like thing happening already. Right, yeah, I've actually just rewrote that. So this can be this part, this part is a repetition of this part. So we put like this instead. And here, this can be rewritten as like this, where this comes here, right? So kind of like a recursive relationship between delta L minus 1 and delta L, right? So once you calculate this, then you can reuse them to calculate this here, and then you can reuse them to calculate this here, and then you can reuse them to calculate this here, and then you calculate. But unfortunately, here there's no learnable parameter theta anywhere. There's no theta here, no theta here, no theta here. So there's no reason for us to do delta L times A L minus 1 transpose to get the gradient of C with respect to W. We don't have to do this here, but you can imagine if there was some learnable parameters anywhere inside this node, then you can do this and then update your parameters. Right, so this is how it's done in PyTorch. You can actually, since PyTorch is an open source project, you can actually go through all these, how this Autograd is done line by line in the source code and see how it's done. It's the core philosophy is not too different from the very simplified version here. And you can actually write your own PyTorch operations. If you need one, you can write one, and then, as I said, you need to write the mathematical operation and the derivative at the same time so that you can plug into the PyTorch library, and then the library will recognize it as a proper Python operation. PyTorch operation, and plug it into the backprop node, backprop process. All right, so this is it. Any questions so far before we end?
Actually, no. This good question. This Thursday, we're going to do this PyTorch practice exactly like this. We're going to start with logistic regression. We're going to add a hidden layer and then do backprop. And we're going to use Colab, so no need to install PyTorch on your. I mean, if you have Jupyter, you already have PyTorch anyway. So, and if you don't have your own Jupyter notebook, we're going to use Colab anyways, and the Colab comes with PyTorch, so you don't need to install anything. Good question. Any other question before we end? 혹시 질문 있으실까요? 네네.
저희 출석 규정이 정확히 어떻게 되죠?
출석 규정은 그 클래스룸 읽어보시면 있습니다. 그거는 클래스룸 읽어보시면 되고요. 저도 뭐 몇 가지 규정이 있어서 기억이 안 나니까 거기 자세히 써 있습니다.
감사합니다.
높아지는 말씀드리는데 혹시 아직도 클래스룸 가입 안 하신 분 있으면 꼭 하세요. 제가 KLMS에 따로 이제 공지를 안 하기 때문에 클래스룸에 다 공지를 올리고 모든 매테리얼, 모든 비디오, 모든 뭐 코드 다 올리기 때문에 거기서 이제 받아가셔야 됩니다. Alright, I'm gonna wait 5 seconds before we end the class today. All right, no question then. All right. Thank you very much for listening, and I'll see you guys. Oh, actually, the TA will see you guys this Thursday. If you have any question, please post them on Classroom anytime you want. All right, thank you very much. Bye-bye.
감사합니다.
네, 감사합니다.